Okay, welcome back to this course on deep learning for advanced vision systems. Today we're going to cover convolutional neural networks. The slides have been prepared by one of my postdocs, Dr. Rahmani. So this is the outline of this section of the course. So we'll start with an introduction. We'll talk about the typical CNN layers, namely the convolutional layer, the nonlinearity layer, the pooling layer, normalization layer, the loss function. We talk on how to perform training for CNN, and then the different regularization techniques used for CNN. And then we'll look at some applications of CNN for computer vision. So how do we want computers to deal with our data? So these are some of the operations we perform. So if you have a car, you want to have a system which would automatically tell you this is a car, this is an airplane, this is a motorbike. And then you can classify into different types of animal, for example. So you can have a classification between people, animal, cars, and so on, or you can have intra-class or intra-class or inter-class, so between classes or within the same class. So for example, you want to, within the class of animals, you want to classify cat from dog from another type of animal. In addition to the classification, you want to also do the localization. You want to do the object detection, so recognition, tracking in the case of motion, and a lot of other operations for computer vision. One of the other applications would be semantic segmentation, again, as we explained before. So you want every pixel to be labeled. So all these pixels belong to the class, road. So you'll have them in this color. These are sidewalks. So you would have them in that color. The sky is gray. You have it in this color, okay? And the cars, so the cars are blue or purple. This sidewalk is blue. So all the pixels which belong to that class are labeled with that color. So from all these operations, what do we need to do? We need to first, so in order to develop a machine learning or a deep learning system, we would like to extract the features which are relevant for us to do the classification, and then also design a classifier to do it. So it is hard because, first of all, we need to see, this is what the computer sees, it only sees numbers, the gray level values. So at this pixel here, it's 125, at this pixel, it is 14, and so on. So the computer would see only these features, these numbers. And we want to process them to be able to extract features, whether they are geometric features, whether they're color features, whether they're texture features. And we would like to take or go to a feature space where it is easy to classify or to devise or to come up with decision boundaries to separate the classes. And so this requires feature classification, as we said before, and then a classifier to handcraft these features, whether they are gray level features or textural features like the text tone, or spin images which are used for point clouds, or other type of features. It is very hard to come up with these features. It requires expert knowledge. It is time consuming to come up with these features. And a lot of time is spent tuning the features, which are often, which are, as I said, in this case here, they're handcrafted. So what you'd like to do is to build a system which is able to learn these features. Okay, so as we've seen here before, so this would be your input image. So instead of pre-processing the image, extracting the features, selecting the features, and then build a classifier to tell you whether this is a car, a sports car, or an animal, or this, then instead of doing all these things step by step, meaning finding the best pre-processing approach, or doing extracting the best features, selecting among these features the most suitable features and so on, we would like to replace all this block here with just a feature learner, okay? So this feature learner would learn the features and the best optimal features which would allow us to perform inference or recognize the object or perform operations. So for this, before we've seen multi-layer perceptron, which operates on vectors. Now we would like to operate on images directly, and this is the objective of introducing the convolutional neural networks. So convolutional neural networks are also known as convolutional networks only, CNNs, or ConvNets. They specialize for data having grid-like topology. So as I said, they're ideal for matrices. So they are, as you know, an image is not more than a matrix where the entries of that matrix are the pixel values. But then you can also use, so if you use a 2D convolution, a 2D CNN, so you can perform operation you can perform convolution on or you have 2D CNN on images. But if you have only a time series, like a vector, you can use 1D CNN. If actually you have a volume image, like an MRI or CT, you can use 3D CNN. So it is suitable for a tensor type of operations. Like, as you know, a tensor, a scalar is a tensor of dimension 0. A vector is of dimension, tensor of dimension 1, a matrix of dimension 2, and then you have higher order tensors. So you have vectors, tensors, so they're of the same family. Convolution, so this is basically a neural networks, so where you need to learn the weights, just like the case of the multi-layer perceptron. But then it is based also on a convolution operation, okay? So it's a specialized kind of linear, it's a linear operation of specialized kind of operation. It's a linear operation, meaning that you perform convolution, which is used a lot in signal processing and image processing and so on, where you perform, it's an operation between two signals. So for example, your image and then a kernel image. And this kernel image has a certain operation, for example, to detect edges or horizontal edges or vertical edges and so on. And this operation, just like when you have addition, subtraction for the real numbers, so this is an operation between signals, and then this is a linear operation, okay? You can prove mathematically that it is a linear operation. So a CNN has a typical number of layers. So you have your input image, and this is your output, but between them, so you have the convolutional layer, okay? You have the nonlinearity layer. So this is similar to when we had the activation for the multi-layer perceptron, and then we had a sigmoid, which is a nonlinear function that would allow us to perform classification, for non-convex regions in the feature space. So we need some sort of nonlinearity here. We also need a pooling layer. We're going to explain what it is, which is optional, but most of the time it is used in most of the architectures used, CNN architectures used to solve computer vision problems. We need also a normalization layer. We can We will explain what it is. And we would have a number of layers in between. So for example, we have a convolutional layer, nonlinearity layer, pooling layer, normalization, and the process is repeated. Or there are variations here in this case. We also have a fully connected layer, which is, or layers, which is just like the multi-layer perceptron that we've seen before. And then we have a loss function, as we're going to explain in the training later. So just like the multi-layer perceptron, we have a data set, we have an input and the corresponding ground truth or label, and then we feed that input, we compute the loss function, the loss that we have, or the difference between the output and the desired, or the desired output and the input, and then we feed this loss here to the different layers to train or to modify the weights. And then the output. Okay, so let's start with the convolutional layer. So the convolution operation, as I explained, is just like an operation instead of the addition and subtraction between real numbers. We are looking at an operation between signals. So convolution is an operation of two functions. The convolution of x and w, written as x and w, is defined by this formula. So x is our input signal. W is actually, it is good that it is written here as W because they correspond to the weights. This is what you want to learn. You want to learn, so this W is also called sometimes, or actually in signal processing and image processing, a kernel. So you would like to learn the kernel. So this is the simple operation. So for each time t, you take the signal, and then you take your kernel, you flip it. That's why this minus a here, and you perform some sort an integration here between the two, and then you shift. You go to, so that was for time t1, and then you go for time t2, for time t3, and so on. So this would be the result at a certain time t. So you take your function at that point, or your input signal at that point, you take the kernel, you flip it, and then you perform the operation. We're going to see more about that. This is in the case where your functions x and w are continuous. But then if they're discrete, then you would replace the integration with a summation. So it's minus summation from minus infinity to plus infinity. And you can view this as a weighted average operation at every time. So you're weighting, sort of, you're performing you're associating. So for each value of xa, you're giving it a certain weight, okay? So for a 2D image I and a 2D kernel k, so instead of calling it W as before, we call it this now k, which stands for kernel. And we are operating in 2D, in the 2D case, not in the 1D case as before. So our image is, so this is the pixel location MN. And we take the kernel, we flip it, okay? And then we perform this operation as we're going to see. So an example to clarify how to convolve in 2D space. So this is your kernel. So these are the values of your kernel. And then you have the corresponding value at this location of the kernel. You have A, B, C, D, E, F, G, H, and so on. And then this is your image. So you're starting at 0, 0, 0 here. We're going to explain more about this -1 here. This is when we have the padding, the 0 padding. So again, we are going to perform this operation. So for S11, this would be the operation. So in this case, what we do, so for S11, this is, so we replace ij by 11, and then we have this operation. And this is because of this operation of the summation. So we're doing this operation. So we're flipping the kernel, So these are the value of the kernel A, B, C, D, E, F, G, H. We're flipping the kernel so that it becomes A, B, C, D, E, F, G, H, I. And then we put the kernel or locate the kernel at the center at 1, 1. And then we look at the I. So for K11, which is this value here, we multiply it by this one, plus this multiplied by this multiplied by this multiplied by this, and we sum the results. Okay? So there is a relationship between convolution and cross correlation. So actually they're equivalent. So convolution is equivalent to flipping the kernel K in both dimensions and applying the cross correlation. So what you do basically is you flip it for the convolution, you flip the kernel. In the case of the cross correlation between the kernel and your image, you don't flip the kernel. And then in the case where the kernel is symmetrical, then the cross correlation is equivalent to the convolution. So let's look at an example in the gray, for a gray image, gray level image. So grayscale input image I and the filter kernel K0. So this is a filter. So this is your input image, which is say a 5 by 5 or whatever. So actually you have a number of pixels here. And this is a 3 by 3 kernel, okay? Usually this, I think for better illustration, it would have been better to have a kernel like -1, 0, 1, -1, 0, 1, and then that show you how this kernel here detects the vertical edges. But just this is just any kernel. So what we do, so assuming that this is an image, which is 5 by 5, so 1, 2, 3, 4, 5 pixels here, 5 pixels here, and we want to perform the convolution with this kernel here. So what we do is so we assume that this is a flipped one, and then we bring the kernel to this location here. Okay, because this is a 3 by 3, this is a 5 by 5. We take this 3 by 3 kernel, we place it here. And then we perform this operation, 0 by -1. And then here is 0 multiplied by 0. Here is 0 multiplied by 0. And I flip this one, I skip this one. And then 2 multiplied by 1, 0 multiplied by -1, and 2 multiplied by -1. So I do all these multiplications, element-wise multiplication. I get the result, and then I sum the results. I perform the addition, because remember I had an integration or a sum sign in my formula. So I get the 1. So I put this one here. And then what I do is I move my kernel to the next position. I do the same operation. I move to the next operation. I move, and so on, until I've reached the last possible location of the kernel. That's it. So here, that's it. I got the minus value, -1 here. Now, what do you notice here is that first thing to notice is that I started with a 5 by 5 image, and then I multiplied by kernel, a 3 by 3 kernel. I ended up with a smaller image. I would have liked to have a 5 by 5 image at my output, but then this shrinked. So there is a problem here, and we'll see how to cover it. Now, if you're given an RGB input image and a kernel filter, so your RGB has 3 channels, the R channels, the green channel, and the B channel. And let's say you want to convolve it with a kernel. So this is a 5 by 5, 3 channels. So each channel has a 5 by 5 image. And then we have a kernel, which is a 3 by 3 and 3 channels again. So this is a 3 by 3 channels. And of course, the values for each channel do not have to be the same. They're different. So how do we do? So this is our 5 by 5, 5 by 5 for the red channel. 5 by 5 for the green channel, 5 by 5 for the third channel, okay? The same thing. So we want to perform the convolution between this RGB image and this kernel. So what do is we align the filters. So this was the first filter. Now the second filter would be aligned with the second channel, which is the green channel. The third filter would be aligned with the blue channel. And then we do the same operation, okay? We do this, okay, multiplied by this, element-wise multiplication. And then we sum this. We add them. So this is the summation here. And then we move our kernel. So it was located here. We move it to the next level. But then before we got this summation here, we add that as well to have our first output value. We move it, we perform the same operation, we get the output, and then the same thing for the rest. Now again, notice that our output has shrinked. So it went from a 5 by 5 to a 3 by 3. And then we had 3 channels at the input. We have 1 channel at the output only. So there are some variants of the basic convolution function, and these variants are related to the stride. Is the amount of downsampling. We're going to explain very easily what it means. The zero padding, which avoids layer-to-layer shrinking. So I remember we've seen that the output has shrinked. So this zero padding would allow us to avoid this shrinking. The ensured convolution, this is like the convolution but without sharing the weights. We explain that later. And the tiled convolution, which cycles between shared parameter groups. So let's see the convolution with one stride. Remember when we had our kernel, which was superimposed here at this location, and then we moved with just one step to the next location, and that means that it's a stride. It's stride 1, but we could move to, instead of moving from here to here, we could move by two strides. We could have jumped, instead of just jumping by the 1, we could have jumped by 2. Let's look at this is the convolution with stride 1 again. So we're moving with sliding the window by 1, okay? 1 vertically, 1 horizontally, 1 on the side, 1 on the, 1 from up to down. And then we're getting and notice for a stride 1, this is a 3 by 3 output. So it shrinks again. Now this is stride 2. We jump two things, two locations. So again, it shrink to a much smaller output. So to avoid this shrinking, what should we do? We should do a zero padding, which avoids this shrinking, you know. Why we use it? Because it showed that it improves the performance. And without zero padding, the inputs, if we don't add zeros to our input image, which is zero padding, the size of the volumes would reduce by a small amount after each convolution. So, because remember, we have different number of convolutions. If you don't do the zero padding, your output after the first convolution would shrink. And then after the second one, you shrink. After that, you won't be able to do any more convolutions. So you need to do zero padding. And the information at the borders would be washed away too quickly. So we would lose the information around the borders. We would lose a lot of information. So zero padding is important. How do we do it? So if we have a 5 by 5 and we want the output to be a 5 by 5 as well, so what we have to do is zero padding. What does it mean? Is, see, we had a 3 by 3 here. We would make it a 5 by 5 and we add zeros all around. That's why it's called zero padding, okay? There are other padding techniques, but then we use the zero padding for the CNN. And then we do the same operations. So now this was our original image. So instead of putting the kernel here, we'll put it with star here at this location, as you can see. Okay, and we get this output. And then we move one stride by one stride, and we get the second output, third, fourth, and so on. Sorry, it's not showing the corresponding score. Okay, now after a number of operations, after all these convolutions and so on, we end up with a 5 by 5 output image. Thank you.